We know of over 6,000 exoplanets out there, and they've been discovered through a range of methods: the radial velocity method, astrometry, the transit method, even direct imaging. But we know of 0 confirmed exomoons. There have been some candidates, but still we don't have a good enough observation that the astronomical community can agree that yes, indeed, an exomoon has been found. And this is because it's already difficult enough to find an exoplanet. To actually find a moon orbiting around an exoplanet is just like orders of magnitude more difficult. But there have been some really good ideas on how you might find an exomoon. And so my guest today has been thinking a lot about this. So today I talked with Dr. Thomas Winterhalder. He's a postdoctoral researcher at Leiden University and released a new paper where he talked about how one of the most powerful interferometers in the world, the Very Large Telescope, and specifically the Gravity Plus instrument on that telescope, can make measurements of exoplanets with such precision that you should be able to detect the presence of an exomoon orbiting around it. So if this is interesting to you, here's my interview with Dr. Thomas Winterhalder. Thomas, we're talking about this in late 2025. Right now, how many exomoons does humanity know about?
Well, unambiguously none. There are some candidates.
Yeah.
Sorry?
Confirmed none.
Yeah, none. So there are some candidates, but yeah, there's been papers kind of talking about these detections and calling them into question. But maybe very soon we'll find one. I guess it's kind of just on the edge, just on the verge of finding one. It could be imminent, but then again, it might take another few years. You know.
I mean, we're here in the solar system, and there are dozens, if not hundreds, of moons around Jupiter. Actually, you know, when you think of the whole solar system, or Saturn, right? Like there are hundreds and hundreds of moons in the solar system. It feels inevitable that we're going to find them. They're out there,
right? Yeah, that's basically the argument, right? That makes this whole search so compelling, because in a way we kind of know that they're there. But yeah, it's basically a race to find the first one, and then probably they'll be tumbling out one after the other.
Yeah, in the same way with exoplanets.
Exactly.
But describe give people a sense of why finding a moon around an exoplanet is like an orders of magnitude more difficult challenge.
Yeah, so basically you're looking at much smaller signals. We're all talking about signal to noise, of course, in astronomy, and whatever method you're using, be it photometric or astrometric, what we are looking at, the signals are just way smaller, and we really have to build the instrumentation first. And now we're kind of at a point where it might work soon, but we still have to pull it off. So that's probably why.
You know, my audience is very familiar, I think, with Dr. David Kipping and his Cool Worlds Lab. And he just came out with a big video and talked about how they tried to use the transit method using James Webb to be able to find an exomoon around one fairly nice candidate. There's another paper that we reported on. People used the Very Large Telescope, the gravity instrument on that, to try and do an astrometric finding of an exomoon, watching the wobble of the planet and the moon, the wobble of the moon on the star, and made a candidate announcement. But you know, obviously this is going to be met with a certain amount of skepticism. Now, your paper was more theoretical. What are you proposing?
So basically, the second paper you mentioned, that paper basically uses the method we look at in our paper. So what we're trying to do, or what we're looking into, this is basically a feasibility study, is to detect it astrometrically. So by the movement or the position of the planet, we want to kind of tease out the wobbles that you would expect from a moon orbiting a planet, or a planet that is orbited by a moon. So basically, if you take the example of a star that's orbited by a planet, of course we've been doing this a lot with stars and planets. So basically, looking at the orbital reflex motion of the star as it is kind of orbited by the planet, And by that movement, which is very small, actually, you can then infer the presence of the planet without ever seeing the planet, right? And here, this technique basically tries to apply this method to like one step deeper to the planet itself. So monitoring the position of a planet relative to its star over long periods of time or a certain period of time, taking measurements again and again, and then trying to see if there is some non-Keplerian or some residual motion there that cannot be explained by two objects in orbit around each other. And that would then hint at the presence of a moon. And this would then kind of manifest as this wobble motion or this epicyclic motion on top of the actual planetary orbit around the star. But what you need to do for this, of course, is you need two things. First of all, you need to be able to actually directly detect the planet. So actually collect the light that's coming from the planet directly, so as to make a measurement of its position relative to the star. And then also what you need is extreme precision in that measurement. So you need to be really sure, you need to be really precise in your positional, your astrometric measurement, because otherwise these reflex motions, they're so small that you would not see them. So I guess one of the kind of the twists in this paper is that we're looking at the possibility of doing this not with a normal imaging instrument, but with optical interferometry, because this specific field of astrometry is something where optical interferometry really excels and where we can use it to the best advantage, because it's orders of magnitude better than what we would get with a normal telescope imaging instrument.
And so I guess, you just hit one of my audience's favorite terms, which is interferometry. So explain the setup then, telescope-wise, on what it's going to take to be able to make that kind of an observation, because you're not just measuring the star, you're actually measuring the planet. And the downside I know of interferometry is if the object is faint, then that makes it very hard. You get the resolution, but you don't necessarily get be able to resolve the faint objects.
Yes. So I saw that Nick Scott was on your show recently.
About the CHARA Array. Yeah, exactly.
So CHARA is one of the big facilities doing optical interferometry. The other one is the VLTI, the Very Large Telescope Interferometer, and this is the one we were looking at in this study. So at the VLTI, we've got an instrument called GRAIVTY, and GRAIVTY is built for this. You can basically say it's built for doing this kind of stuff. What it was actually built for is to look at the galactic center, and actually the group that built it won the Nobel Prize for the science they did with gravity. That's how cutting edge it is. And what we're using it for is actually doing this kind of stuff, looking at planets. And with gravity, we can achieve insane astrometric precision. So we're looking at on good nights, 50 microarc seconds of astrometric precision. And that's because of the baseline we get, right? We have 4 big telescopes, 4 unit telescopes in Paranal, so at the Very Large Telescope. And they are separated something between 50 to 130 meters in baseline. And that's really where this awesome power comes from, because precision scales with the length of the baseline and not the size of the telescope. And actually CHARA has longer baselines. So in principle, you could do this even better with CHARA, but it is also much more sensitivity limited. And that's the other thing you mentioned just now, right? So because the telescopes in the array are smaller, we would not be able to see these planets that we're interested in to actually look for moons. But with VLTI, we can, because we have 4 8-meter class telescopes. And that gives us the sensitivity and the contrast capabilities that we need to do this kind of study. So basically that's the two things. We have sensitivity and we have baseline.
Right. You have the separation, which gives you that resolution, and then you also happen to have 4 of the biggest telescopes in the world connected together into this network, and so that gets you to be able to the ability to look at those faint objects. And I think, when we think about discovering planets with astrometry, we're looking at the wobbles of the star and then the influence of the planet on the star. And in this case, you're saying, no, let's look at the planet and look at the wobbles on the planet from the influence of the moon, which is just next level. And so, according to the study that you did, the calculations that you made, what are the kinds of moons that you think are within the grasp of gravity?
So yeah, that's a good question. I get that question a lot when I present this at conferences, actually. To be honest, these would be, like with any other moon detection method at the moment, these would be rather extreme cases. So we're looking at what we call irregular moons. These are moons that are thought to form as a consequence of a collision, for example, or as a consequence of capture, both of which we see in the solar system as well. So probably this is also happening elsewhere. For example, our own moon, so Earth's moon, formed after a collision event. And you've got Triton as an example of a moon that was captured, and you can see it in its weird orbit around Uranus. No,
Neptune. Yeah.
Yes.
Yeah. Like it goes backwards from the rest of the moons in the solar system. Yeah.
So both of this we expect to happen. And this means this gives us an opportunity, basically, because from a in situ formation, so in the circumplanetary disk, which is what you would expect to have happened with the Galilean moons, that has kind of an upper limit in mass ratio between the planetary host and the moon. And these regular moons, they are very hard to find because they are, compared to the planet, they are tiny. But with these irregular moons, we can it's a kind of trick for us to be able to at least expect that we should see higher mass ratios, and therefore we should be able to see them today with our current instrumentation. And that's the ones we are currently sensitive to with gravity. So these would be moons with mass ratios relative to the planet of 10 to the minus 2 to 10 to the minus 3. It depends a bit on how you apply the method, actually, because this is very similar to what you do with radio velocities to detect planets. What you do there is sometimes you find yourself in a position where your signal to noise of a single epoch, so a single measurement, is rather low. But if you just pile up measurements, if you pile up epochs, so let's say 20, let's say 30 measurements monitoring the system, you can build your significance. And this is the same with the astrometric method and with our method of moon detection. So depending on the number of epochs, you can vary that kind of estimate. And that's also something we investigate in the paper. But we are looking at these irregular moons for now.
Mm-hmm, mm-hmm. And so is it kind of like the equivalent of like hot Jupiters were what exoplanet scientists found first because they're just extreme. You've got this giant planet that's very close to the star. It is putting a lot of sort of gravitational tug back and forth, and it just pops out from the radial velocity method. And then it took longer to find smaller planets, M-dwarf planets, things that are, and we still haven't even found what's very similar to the Earth yet. And so are these irregular moons kind of the hot Jupiters of exomoons?
I think that's a very valid comparison. It's basically the low-hanging fruit. So These are the most extreme cases and the ones we expect to see first. But whether or not they exist, or whether or not they exist in this parameter space, we don't know yet. And that's why we have to look, right? We'll only find out if we look. And we do have models that model this, but this can also be, these can be data points for these models, right? So it can, in a way, inform the theorists by eventual non-detections or eventual detections. We'll have to see.
But there aren't a lot of exoplanets that can be resolved directly. I mean, that in the beginning, you need a very specific type of planet at this point, even with the VLT.
Yes, for sure. So we've got a few dozen maybe that we can actually look at with gravity. And actually, just as a side note, even without the kind of moon science case, looking at these planets with gravity is is really special because by that astrometry, we can then constrain the orbital solution of the planet around the star and get masses. And so even if we do not find these moons, having many data points will give us very precise orbits, very precise masses, and that's something we're also lacking in exoplanet science. But you're right, there's not too many of these planets that are kind of viable for this method. But there's something big coming, and that's the ELT. So just half an hour away from Paranal, the biggest telescope in the world is being built right now. And with that, we expect the number of directly imaged planets to rise steeply. And then, of course, if they're at the right separation, we will also be, and the right contrast, we will also be able to follow them up with gravity. So it's kind of gravity and the VLTI, they will not be obsolete once the ELT comes around. This precision measurement, this crazy accuracy in astrometry will not be given by the ELT, for example. But there are kind of symbiosis. There is a symbiosis between the two facilities for sure.
Right. And do you get any constraints on the orientation? Because like the big downside of the transit method is that you need to have this alignment of the star, the planet, and I guess the moon, and then our perspective from Earth. Do you get a lot more leeway when you're using this method with astrometry?
I guess so, yes, because first of all, it kind of, there is no condition on the orbital geometry of the planet, star-planet system. So that's one thing that will increase in a way, it will increase our sample size. But then again, of course, there are way more planets found transiting because of the facilities we already have and how prolific they were in finding these planets, right? But yeah, so in a way, you could say that we are less constrained. But the truth is, I think the fact that we don't know so many directly imageable planets right now kind of acts as a stronger constraint than what we loosen by not having to go for the aligned ones. But then again, the planet moon system, there's also no constraint there, right? So basically, if there is a moon around one of these directly detected planets, and it's in a regime where we can, in a mass regime where we can, and a separation regime where we can find them with this method, then we will find them. It doesn't matter how inclined they are, because the wobble we see, the projection of the wobble, it doesn't matter if it's face on or edge on, we will see that wobble, and the astrometric signal, the amplitude will be the same. It's true that if it's very inclined, so if the wobble would be in one line, basically the planet would move back and forth along one line, then we would probably need more epochs, more measurements to find it. But it will be detectable just as it would be if it were face on.
Right. So you're either getting the planet going back and forth because of the influence of the moon in your observations, or the planet is making little circles. Exactly. As it's going around the star, and you get the influence of the moon either way.
Yes, and there is one additional thing that is probably that might be interesting. If we have a very inclined orbit, if it's along a line, let's say, we do get these moments in time when the planet is exactly where you would expect it to be, even without a moon, and that's dangerous because if we take an epoch at exactly that moment, and we take another epoch one period after, then we would always see it at the position where we would expect it to be. And then we wouldn't be able to detect the moon, or we would say there is no moon there, even though there is, because we sampled our time series. So our kind of data set is sampled in the wrong way. And that's kind of a pitfall that we need to avoid. And it's actually not too tricky to avoid it. You just have to vary your cadence. And if you do that, then you will avoid that pitfall. But with the face-on moons, you will always have a certain astrometric signal, because the planet will always be removed from the position you would expect it to be if there were no moon. So if you do the model comparison, you would always have some sort of signal within those epochs.
And I mean, obviously, you're getting, planets are going to have multiple moons. And so, do you, or in many cases, I mean, we have the moon, but Jupiter and stuff, as I said, hundreds. Do you, and I mean, right now you're finding these irregular ones. And so do you think that it's, you're going to get one irregular moon around a planet? Are you going to get multiple irregular moons? Are you going to see weird variations in multiple moon systems?
I think the expectation is that you would see one. At least, I mean, this goes back to this low-hanging fruit thing. You probably do have, if you have one, you probably also have some minor ones if you're looking at a gas giant planet. But the problem is that those minor ones, they leave almost no signal. So you would be, the first systems we would find would be ones with one moon that has a rather high mass ratio. And then also you run into problems with degeneracies when you have several moons, and they might kind of cancel each other out in terms of the signal they produce. And especially they are drowned out by the major moon. So I would expect that the first ones we find, we see one signal and then some noise on top of that probably. And that noise might be additional moons, but it might also just be noise. So yeah.
An exciting idea would be a binary planet. Would that pop out of the data?
Right. So that's actually probably the lowest hanging fruit. So because this is, in a sense, it's the same system configuration. You have a star, you have a planet, and you have a companion to that planet. Whether or not that companion has a mass ratio of 1% or 1/10% or 25%, which you would probably then call kind of a binary planet system, it doesn't matter for the method. The method will detect these configurations if they have the right mass ratio, the right separation, if we are sensitive to the configuration, and then it's really a matter of definition, right? So you could talk of a binary planet, but there's mass ratios in the solar system as well between Pluto and Charon, if I'm not mistaken, have so it's not a planet anymore, but still a dwarf planet and its moon of 12%. So is that actually a binary dwarf planet, or is it a dwarf planet with the moon? Also, the Earth and the moon have 1%. So it's also kind of massive. And these definitions, I think, we haven't really come up with a proper definition of what is a binary planet and what is a moon, but it doesn't matter to the method. And both would be interesting to find.
Yeah, that would be pretty amazing. And so, is it right now that there aren't enough candidates, or not enough time has been dedicated examining each of the potential planets to really make a confirmation?
Do you mean for moons in general, or for moons?
Yeah. Like you mentioned, we talked earlier on that you said maybe there's like 25-ish planets that have been directly observed that are sort of within the capabilities of that. When we know of 6,000 plus exoplanets, mostly found through the transit method, 10,000 plus candidates. Like, there's a lot of planets out there, but you need that separation. You need a fairly large planet going around a star that's not too bright. Like, you put a lot of constraints, and we only know of a handful of directly observed exoplanets.
Well, I think in a way that's true. In a way, having more planets to go on is obviously better, but there is also an argument to be made that some planets are better than others, in the sense that you would expect the survival of moons around planets to be different, depending on the orbital configuration of those planets. So if you're close to the star, your Hill radius, so this is basically your sphere of influence around the planet, will shrink because the influence of the star will increase. And therefore, planets closer to stars, so separation-wise close to stars, they would be expected to not be able to hold on to their planets so well, because they would have to be bound closer. And if they're bound closer, it's also more likely for them to be torn apart. So this is why you would expect planets with short separations to host fewer moons, or at least host fewer moons that survive until we can actually detect them. And this is why, yes, we do have fewer planets or directly imaged planets that might be viable kind of planet moon hosts, let's say, but they might be more favorable in the sense that here we actually expect moons to be still present because they haven't been ejected and they also haven't been torn apart. So in a way, targeting the directly imaged population might be a better way to go.
Yeah. Well, I'd like to shift gears then and chat about just interferometers in general and your experience with the Very Large Telescope. So give us a sense. You sort of talked about this idea that, these telescopes are separated up to, what do you say, 140 meters?
Yes.
What's it like using an interferometer like that as sort of an experience as an astronomer?
So the experience of using it is probably not that different to the experience of using another telescope, a single telescope, for example, because mostly it's online anyway. So you would be remote observing if you're lucky enough to get time on the telescope. But yeah, I think the main difference is comes afterwards. So basically, the data analysis you have to do, the pipelines you run this data through are very different. So your interferometric setup or this technique, this mode of observation is way more intricate, I'd say. It's you would have to go through many more motions to actually pull out the science from the data. You're looking at different observables, so you're not looking at you're not looking at your traditional kind of astronomical observables. What we're looking at is closure phase, fringe phases, fringe amplitudes. So it's a very kind of niche field. It's a very specialized mode of observation, but it obviously comes with its own kind of benefits in the sense that we can access parameter ranges that are not accessible to other telescopes. And we also, as we already mentioned, have precisions. We're working with precisions, angular resolutions, and astrometric precisions that are orders of magnitude better.
But when I think about, say, a radio interferometer, like with the Event Horizon telescope, like they were gathering their data separately at each telescope. They had atomic clocks, and then they brought it in together into the central place and then compiled the data together. But you can't do that with an infrared interferometer or with a visible light. It's got to be done while the data are being captured by the telescopes. And so it's not like you get data from 4 different telescopes and then you have to merge them and come up with your answers. That had to be done correctly by the telescopes and the setup. And so I'm sort of imagining like what it's like to be there and you're like, did we get it? Like, did it come together in that way that we need? In the way that you can't just fix it afterwards and, we messed up our process. Okay, run the analysis again. It's baked in because it had to be done while it was captured.
Yes, so that's exactly right. So compared to radio interferometry, this is more intricate. It's more like hands-on. It's a physical mode of actually producing interference fringes, right? So we cannot. Basically, the problem is that we cannot really measure the phase of the light when it's coming in because it's too quick. And you can do that with radio telescopes, and you can do that with arrays of radio telescopes. And this is why you can record your data and then later on do this kind of virtual interference. And we can't do that. We have to do it physically. So we have delay lines, we have optical fibers that transport the beam. So the infrastructure is way more intricate and it costs more money. And it also, maintenance is a big thing. That's the main difference. And during the observation, you would have metrics that tell you, okay, this worked well, this didn't work well. We lost fringes, for example. You would get notified that happens, and then you would have to go through the motions again. And that does happen, actually. So it's not like this is rare. It's actually a common thing to happen during the night. And
Yeah, I mean, I sort of imagine like with a lot of telescopes, you just provide the coordinates, you provide the times, you provide the wavelengths, you talk about the filters that you want, and then you come back later and the data are there waiting for you in a Dropbox, and you pick it up and then start to process it. But it is, when you're doing your observations, it's much more of a kind of a live event, and there's got to be people there who are turning knobs and watching it and making sure that your observations are coming together as you intended, because it's a special mode of these telescopes. And then other times they're on their own individually looking at different targets.
Right. There's one more thing to be said here, though. Most of us observe in service mode. So we basically we write little programs, little pieces of code that actually we send to the observatory, and then that gets executed while most astronomers in Europe, at least, if you're observing in Chile, are already asleep, or actually, no, while they're already up again. So the hands-on actual experience probably doesn't happen, because that's actually done by the telescope operator. So if you're very lucky, you get to go down there to Chile, and then you will see all this, what you've just described. And that's really, you have to be really lucky to see that. Yeah, but normally it's in service mode, because for the observatory, it saves a lot of time and money to not fly everyone down there, and time in the sense that they would schedule.
But even... Yeah, I mean, I sort of even imagine it though with the telescope operator, right? Like it feels like it's a different event when you're just pointing this giant telescope at one target, or when you're trying to coordinate all 4 observatories and you're trying to bring the lines together and keep them all in phase. Like, it just feels like it's a totally different experience.
For sure. And nowadays, it's actually, one more thing to add here is nowadays it's way more of an event as well, because we recently had the GRAIVTY Plus upgrade. So this basically installed laser guide stars on all 4 UTs and wavefront sensors on all 4 UTs. So we can do AO correction on all the beams. And this, first of all, it increases our signal to noise a lot. But what it also does is when you're there, you actually get to see the 4 telescopes with 4 laser beams pointing at the same target, and that's kind of impressive. So you're very right. It's a very different mode or form of observation, and if you're lucky enough to be there, that's amazing.
Yeah. And I've seen the mock-ups of the ELT with it's got, I forget how many lasers it's got.
I think it's got 8.
8. Yeah. It really looks like some kind of Death Star firing into space.
It does, yeah.
Because the more of those lasers you can put on in the area, then the more you can tune your adaptive optics to capture the area. And so instead of just one star, or in your case, I guess 4 stars, but I guess each telescope is producing its own star, you're getting much more. So it's sort of taking this technology to the next level. So what do you think the future holds? I mean, we're very early on in this process of even knowing where exoplanets are. Nobody has, the scientific community has not agreed that an exomoon has been found yet. But, as this plays out into the future, do you think astrometry is going to be doing like the lion's share of exomoon finding?
That's a good question. I'm not so sure about that, to be honest, because this method, like the RV method, for example, we made that comparison earlier as well. It requires gathering data over extended period of time, and it requires 12 data points, 18 data points, 24 data points. So if we want to do that for a lot of targets, then that will just require a lot of telescope time. And as with the exoplanets, we've seen this with exoplanets, most of the exoplanets come out of survey missions, right? So this will change as well in it will still be survey missions, but there will be a revolution very soon when the Gaia exoplanets come out, and then we're looking at huge amounts. I think astrometry applied by ground-based observatories on single targets only will not provide the lion's share, but it might just provide the first few ones. We never know. It's we'll see.
Yeah, almost like how radio velocity gave us those first planets, and then transit took over.
Exactly.
Thomas, what are you obsessed with right now?
I'm still working on this. I'm preparing what's called a white paper for the ESO Expanding Horizons call. So basically, this is where ESO looks at what's coming after the ELT, and it would be amazing if we could build an interferometer with huge baselines, because then that would do wonders with our astrometric precision. We're already orders of magnitude better than what you would get with an imaging instrument.
Yeah, their ideas of building much bigger interferometers in that facility, right?
Yes, so we're looking at different ideas. We have we could add a fifth UT, for example, and increase our baseline length, our longest baseline length, to 200 meters, more or less. That would be amazing already. To kind of change the configuration of the array as well a bit. So if you add a fifth one, you could do like a one baseline at right angles with the longest one that we have at the moment, and that would be very good for what we do. But you could also look at putting telescopes on other hills around in the location. Of course, you'd run into problems with the beam transport. You'd have to think of some kind of fiber system for that. But these are ideas that are explored right now, and right now is the time for doing that. So
what's the coolest one? Like, you're looking at it and go, yes, please. That would be amazing if we could actually summon the will and the finances to make this happen. What would that telescope look like?
So that's a good question. I guess having huge baselines with the 8-meter telescope class apertures along those baselines. So this would be called, I think at the moment it's kind of dubbed as a kilometric baseline facility in Paranal. Extended VLTI, some people call it. That would be the coolest one, I think.
So you're saying like they could put another one of those 8-meter telescopes a kilometer away?
Yeah. Yeah, so the fifth UT idea, that would be another one of these 8-meter telescopes. And that would be kind of on a separate foundation. So because the platform is pretty much full. So on the hilltop, on the mountaintop, it's been flattened, of course, in the 90s when the VLT was built, and then the 4 UTs got put there. But now you're kind of running out of space a bit, because you also have the ATs, so the auxiliary telescopes, 1.5 meters. So if you wanted to add a fifth UT, you would have to build some kind of foundation for it. But yeah, that would be 8 meters, and putting that even further away or adding several of these, that would be cool. But these ideas, they have to contend with a lot of other ideas. Like there's teams that have, I would say, that are a bit further in the process of developing their ideas. The WST team, for example, at last is kind of a radio dish, and these will all be contenders for the next facility that ESO builds after the ELT. So I think, it's a contest, but I think we should definitely put something forward in terms of optical interferometry.
Yeah, it would be amazing to, if someone could put one of these on another mountain nearby, and you could be separated
and then connect
by
them.
And be separated by kilometers. I mean, it's the same challenge that they're working with the CHARA Array. How far can you separate these telescopes and still feasibly bring those signals together? And I mean, infrared is a little more forgiving than visible light. Right?
Yes, yeah. So they're looking at, they built this movable telescope where they just drive it off to achieve a longer baseline. But at some point you will have to look at, so I think they're doing vacuum tubes at the moment to transport the beam. But at some point you would have to look at fibers, and then you have a lot more other difficulties. You run into other problems like that you lose a lot of light in those fibers and stuff like this.
Very cool. Awesome.
That would be very cool.
Yeah. All right. Well, Thomas, thank you so much for taking the time to chat, and good luck with your research. And I can't wait. Let us know when you find a moon.
Oh, I will, for sure. Thanks a lot.
Thank you. I hope you enjoyed that conversation with Thomas Winterhalder. It's funny, I should let you know about the timing of this. I actually originally scheduled this interview with Thomas back in September, and then there were issues with his schedule and my schedule, and then I was away for a month. And so during that time, another group made an announcement using the methodology that Thomas was talking about in this interview to announce the discovery of an exomoon. Now, so it shows that the method probably works. It's still too early to have a direct confirmation, but it won't be long now, I think, is where this is going. And then, of course, this is sort of separate from the work that's being done from Dr. David Kipping and his group. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lake Roofing, Brian Bodie, Carabin, Chuck Hawkins, Commander Bailock, Cy Nelson, Darkfinger, Dave Verbath, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Porabach, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. If you sort of enjoy this topic of interferometers and sort of what they can do for astronomy, I think you'll really enjoy an earlier interview. And in fact, Thomas referenced that interview in our conversation here. And this is the interview that I did on the CHARA Array, which is an optical interferometer that is built in the United States at the Mount Wilson Observatory. And just the level of engineering that goes to be able to bring the light from all these separate telescopes together in real time. They've got a room with carts that are moving around on tracks so that they can align the beams coming from these different telescopes as the object that they're looking at is moving through the sky. Like, it changes the distance. And so they actually have to change the length of that the light travels to be able to bring it together and have this interferometer actually come together. And it's a very similar technique that's used at the Very Large Telescope as well, that when you are trying to align these telescopes to do their work together, like one big instrument, it is a gigantic challenge, and some of the greatest engineering in astronomy comes from these interferometers. So definitely go and check out that interview if you haven't already seen it. I think you'll really enjoy it. All right, we'll see you next time.